So now I want to talk to you about analysis of variance, ANOVA. So why ANOVA? Up to this point, we have only been comparing two populations. So of course, limiting ourselves to only two populations, it actually might hinder us. So, what if we wanted to compare the means of more than two populations or compare populations that contain several levels or subgroups? Just suppose we want to compare three population means to see if there's a difference that exists somewhere among them. So, an ANOVA, an analysis of variance, determines whether three or more variations of a factor or treatment have the same effect on a population. So, each sample has a different population mean. What I'm asking is, do all three of these means come from a common population? Is one mean so far away from the other two that it is likely not from the same population? So let's just say I want to go into the potato chip business. I've got three different recipes, but because I'm new to the business and I don't have a lot of money, I can only produce one particular flavor. So I want to see which flavor people like the best and produce that one. So I randomly select 90 people and I randomly divide them into three groups. So one group tries my new barbecue flavor, the second group tries my ranch flavored, and the third group tries my cheese flavored. All participants actually fill out a rating form on a scale of 1 to 7, that beautiful Likert scale, from hating it to loving it. So, or a scale of 1 to 10, how much do you like, which flavor? And now, guess what? I can compare the average ratings of the three groups using the ANOVA. It's a great thing. So in this example, the chip flavor, barbecue, ranch, and cheese is my categorical, my independent variable, and the rating of the taste of the chips is my continuous, my dependent variable. So to see which flavor had the highest rating, I could run three separate independent t-tests. However, running three different tests, there is a higher probability that I make the wrong decision, that I might make it. The more times we make decisions about the significance of t-tests, the greater the chances are that we are wrong. Running multiple t-tests actually increases making a type 1 error when you're rejecting the null when it's true. So a one-way ANOVA actually fixes this by adjusting for the number of groups that are being compared. And we have a couple of rejection rules that I need to talk about. So if the F value or the test statistic is much larger than the critical value, we reject the null hypothesis of equal population means and conclude that there is a statistically significant difference among population means. Also, there's another general rule. As you'll see, if the p-value generated by the ANOVA, that means if p is less than or equal to a, alpha, we reject our null. If p is greater than our alpha, then we fail to reject our null. So as you'll see, we have n, which is going to be equal to our total observations. Our C or K is the number of columns divided by the treatments, and we're also going to use degrees of freedom as well. So let's look at an example. Let's just say a psychologist wanted to compare three methods of reducing anger in university students using a certain test measuring a degree of hostility. So 24 students who are known to have high anger were selected for the study. 8 students were randomly selected and treated with method 1. 7 students were randomly selected and treated with a different method, and the remaining 9 students were treated with a third method. So our independent variable is going to be the three methods of reducing anger, and our dependent variable will be the continuous measurement of hostility. So here are our three methods. These are our columns or our groups, and within each method we are actually going to take a random sample. Why is this called a single factor ANOVA? It's because each method presented is a single factor. All right. So let's consider the anger management test with the three methods measuring the level of hostility. Here we can see our handy dandy box plot. And, what is your preliminary conclusions about the differences in means, medians? Are there any differences in variability, any outliers? So, I mean, kind of think about this. In an Anova, it tests the null hypothesis for each factor. So the null for each factor states that, varying the factor actually has no effect on the population. There is no difference in treatments or methods. At least one mean was different. So what we have to determine up front is what degree of certainty will you require for the Anova test. I know Minitab, it automatically uses 95%, but in Excel we can actually choose. So there are two types of variations compared to the grand mean, the mean of all observation. It's a set of all samples divided by the sample size. Those variations caused by the treatment or method, variations caused by sampling. We have two extreme cases. Case one is where the variations caused by treatment equals 0. The variations caused by sampling equals 1 million. The means aren't the same. Do we reject the null? No, we do not. All right. So, here's another extreme case where the variations caused by treatment equals 1 million, where we have unexplained variation that results in an error. Variations caused by sampling equals 0. Do we reject the null? Yes. All right. Since by definition, Anova is analysis of variance, remember, variance is the average squared deviations, difference of a data point from the distribution mean. It really looks to see how spread out your numbers are. So these are, you'll need to know these. So, we're going to take the distance of each data point from the mean, square each distance, add it all up, and then find the average. In an Anova, we look at total variations, which is the sum of squares, or SS. This is the variance without finding the average of the sum of squared deviations. SS is, is just the difference of the dependent variable and its mean. So we want to look at, these are some definitions you need to know. SSTO, sum of squares total, sum of squares for treatment, and sum of squares total, I mean, we're finding the difference between each data point and the overall mean. We're squaring the difference and then we're adding it up. That's all it is. When we take a distance and we square it, we literally, guess what, get a square. So sum of squares total, just sum of squares for error. So just kind of remember these. All right. So here's an example in an Anova table. Sum of squares between a column. You find the differences between each group mean and overall mean. You square the deviation, you add it up, and in our example, we would have 3 square deviations. SSE, sum of square error, this is about the individual distance around the column median. You find the difference between each data point and its column mean, you square the deviation, and you add it up. All right, and we also look at degrees of freedom as well, and so it should be familiar with this, especially with the t-test that you were doing previously. And here's an example of it in an Anova table. Okay, and we also look at mean squares. Mean squares treatment, mean squares error. These are your handy dandy formulas. MSE is also called sample variance or common variance, and the square root of the mean square error is called the sample standard deviation or common standard deviation. And let's look at what it looks like in an Anova table. So I did these in Excel. So our total here, all this is our mean square for treatment. MST here, this is our sum of square total. MSE, we've got our mean square of error. Here, SSE, our sum of square error. Oh, look at this. This is our degrees of freedom. And also here. Let's look at our F statistic. So MST, mean square treatment. MSE is our mean square error. And so our F ratio is a ratio of two variances, which is the variance of the columns. Okay, so, how do we make our decision? Let's go back to our Anova rejection rules. I'm going to repeat this again. So if the F value or that test statistic is much larger than the critical value, we reject the null, our null hypothesis of equal population means, and conclude that there is a statistically significant difference among those means. Also, there's another general rule. So if the p-value generated by the ANOVA, so if p is less than or equal to our alpha, we reject our null. If the p is greater than alpha, then we fail to reject our null. So we've got to have n, which is our total observations. We've got to have our number of columns or treatments, and we've also got to look at our degrees of freedom. So based on the study that we were talking about with student anger management, in this example, our test statistic was equal to 29.57. Our critical value, alpha, 0.05, was equal to 3.47. Our decision is to reject or null. And you can also find the F critical value in MS Excel. And so this is the function that you're going to use right here. And you just kind of plug and play, or with the Excel spreadsheets that have been set up, you can just copy and paste into the Excel spreadsheet, and it should do it for you as well. All right. So once again, this is our ANOVA table. This is what it looks like. You should be familiar with this. So I want to go over really quick how to set up a box plot in Minitab Express. What you're going to do, you're going to open it, and you're going to enter your data sets as the following. Remember, you've got your names here, and these are your observations, in each column. And then you're going to select that. So in Minitab Express for the box plot, what you're going to do, you're going to select graphs, and then you're going to go to box plot, and then you're going to go to simple, in multiple Y, because we're doing a single set ANOVA. Okay, and then you're going to double click each entity and then hit OK. All right, and then this should be your output. So I recommend practicing that as well.